And let me quickly change the shape. Today's discussion is about recursive time complexity. Means how to calculate time complexity of recursive algorithms. এটা পড়লে আমাদের টাইম কমপ্লেক্সিটি অ্যানালিসিস এর পার্টটা পুরোটা শেষ হবে। We first discussed how to find out time complexity of iterative algorithms. In fact, we started the course with that lesson. And then while studying recursive algorithms, we kind of did an intuitive analysis of complexities. আজকে আমরা দেখবো যে এটা মেথডিক্যালি কিভাবে করে, how to do a methodical calculation of recursive time complexities. I'll give you a quick example of recursive algorithms. Uh, You all know about Fibonacci numbers. Fibonacci numbers, which is a series of infinite integers starting with a 0 and a 1. And every third number of the series is summation of the previous two numbers. So the next one is a 1, তারপরে 2, then 3, 5, 13, 21, goes on. An infinite series. Uh, Generating formula of the series is, uh, let's say we want to find out a number in the series, the nth number in the series. That's what we call fib n. Nth Fibonacci number is the summation of the previous two Fibonacci numbers, fib n minus 1 plus n minus 2, with the base cases of the zeroth Fibonacci number is 0, which is this one, and the Fibonacci number in month place is 1, which is this one. These two are the bases, the starting points of the series, and then this is the generative function. In recursion, if we want to generate the nth Fibonacci number using a recursion, we do exactly like the syntactical implementation of this formula. Let's say we want to write a recursive function which should have the base cases and should also have the general case. Base cases are if n is 0, it's a 0. If n is 1, the value is 1. So we can write it as if n less equals to 1, return n. This will give fib 0 and fib 1. And then for general case, we have to calculate this value here, which will be, let's say answer is equals to fib minus 1 plus fib minus 2, which we can return, right? Now, let's find the time complexity of program. In plain eyes, this may look like a linear time algorithm because I can write the numbers with just order of 1 time complexity. Say, what comes after 21 is 34. I just have to add these two numbers. So it looks like the function should also have a linear time complexity, but it's not. Let's see why. First, we need to write down the time complexity of this algorithm in a generative function. What I mean is the time complexity of generating the nth Fibonacci number, we will call it as T of n. And the value of this should be something which we don't know yet, but we want to figure out a formula which can give us the value. So just because we have to call two recursions to get n Fibonacci number, these should be the time complexity to figure out these values or solving these recursions should be involved here. So we can write the time complexity to find n Fibonacci number should include the time complexity to generate the n-1 Fibonacci number and the time complexity to generate the n-2 Fibonacci number. And we should also write if there's something else. And by something else, I mean what other operations are there in these recursions. There's a conditional checking here, and there's also an addition operation here, mathematical addition, and another statement. But these all should be of constant time complexity. So we can write just a +1 representing constant operations, constant time operations. There goes the generating function of the time complexity of this recursion. And now we need to solve it to get the actual value. We want to find what's the actual value for T of n. Right. The method that we apply to do this is called the substitution method. Substitution method. I'll tell you why the name substitution is in here. First, the formula was T of n is T of n minus 1 plus T of n minus 2. So first, I will do an approximation of this function. There are two recursive terms here. I will assume that both of them are very close to each other. The value of both is very close because it's just a matter of one extra function call. So assuming that, I will write that the function needs to find T of n minus 1 twice. So what I did is assume that T of n minus 2 is almost equal to T of n minus 1. 2 is similar to T of n minus 1. That's an approximation which we almost always do in time complexity analysis. So that makes our formula twice T of n minus 1. Now the actual task begins. To find T of n, we need to find T of n minus 1. T of n minus 1 should be twice T of n minus 2 plus 1. And we also need to find T of n minus 2 for that. T of n minus 2 should be twice. I'm just repeating the same formula for different values of n. I think by now you've got that this needs to go down to 1. The value of n needs to go down to 1, starting from n minus 1, n minus 2. So this will repeat. Say this repeats to 2, n equals to 2. It should be twice T of 1 plus 1. And then we can write T of 1 equals to 1. And T of 1 means the actual base case of the regression when the value of n is 1. Then the time complexity is also constant because we just saw that these are the base cases of our recursive formula. And here in the function, that's also the base case which doesn't have any recursion, which doesn't have any loops. So it's a constant time complexity task. From that, we say the time complexity of base case is constant 1. So in this series derivation, we write T of 1 is 1. So we have all these as information, and now we will use these to find the actual value of T of n. Okay. The next thing to see here is there's twice T of n minus 1. And on the second line, I just wrote one single value of T of n minus 1. So let me multiply this whole line with the 2. So twice T of n minus 1 should be this whole part multiplied by 2. That makes it 2 square for T of n minus 2 plus 1 multiplied by 2. So 2. বাংলায় বলি যে এই প্রথম লাইনটাতে আমাদের টুয়াইস টি অফ এন মাইনাস 1 ছিল, তা আমি এই জিনিসটাকে সেকেন্ড লাইনে লিখতে চাই। 2 multiplied by t of n minus 1 is right side, the whole right side multiplied by 2, which gives মানে পুরোটাকে আমাদেরকে 2 দিয়ে গুণ করতে হবে। So it becomes 2 squared, কোশ্চেনটা 2 স্কয়ার হয়ে গেল, then t of n minus 2 রিকার্শনটা আগের মতোই থাকবে, and then পাশে যে প্লাস ছিল এটা 1 multiplied by 2 2 হয়ে গেল। And now we see that it has become 2 squared t of n minus 2. সেটা আবার এই লেফট হ্যান্ড সাইডে নিয়ে আসি। 2 squared t of n minus 2, তাহলে I have to multiply the right side with 2 square. Sorry. Then it will become 2 cubed t of n minus 3 plus square. So what we are seeing is that in every line, there's a quotient of a power of 2. This line has 2 to the 1 as a quotient. This line has 2 squared as a quotient. And then all the subsequent lines should have a quotient as a power of 2. Carrying it on to the second last line, there should also be a power of 2 as quotient. 2 to the power something will be here. What's that something? If we try to observe this pattern, the first line had 2 to the 0 as quotient, which is actually 1. The second line has 2 to the 1, 2 squared. And we are also decreasing from n and minus 1 and minus 2, going down to 2. This will be very close to n. In fact, this will be 2 to the n minus 1. So you can stop me anytime if you don't get it. So this will be multiplied by 2 to the minus 1 becomes 2 to the n t of 1 plus 1. And then the very last line should have 2 to the n as a quotient. So this one will be multiplied by 2 to the n becomes n. Okay, let me do it one more time for you. This whole page rewritten. So the time complexity written in a formula with the approximation was t of n equals to twice t of n minus 1 plus 1. And then we went on to find the value of twice t of n minus 1, which gives t of n minus 2 plus 1 multiplied by 2, meaning twice t of minus 1, sorry, minus 2, 2, and then 2 squared, and then 2 squared t of minus 2 is, I'll not write the breakdown again, 2 cubed t of minus 3 is 2 squared. So this is a to the power 1, this is 2 squared. And then going down to the very bottom, we will have to find 2 to the power n minus 1 times t of 2, which will be, not writing this down again, 2 to the n 1 plus 2 to the n minus. And the very last line would be 2 to the n t of 1. So this will just be single value 2 to the n. Now, what's here to do is, eventually we need to get the actual value of t of n. If we just add up all the lines in this direction, let's see what happens. So there should be a big left side equals to, and there should be a big right side. Left side should have the addition of all these terms, and right side should have the addition of all these terms. Okay. But the thing to see here is, if we actually add all the terms on the left side and add all the terms on the right side and put them together in a single line, there should be a huge number of deletions. One of them would be, there's a twice t of n minus 1 in the right side, and there's a twice t of n minus 1 in the left side as well, who will both come down to this big line. And then as these two same values are on two sides of a single line, we can delete them. So delete this one and this one. They just subtract each other. Similarly, you can say 2 squared t of n minus 2 will be cut by this 2 squared t of n minus 2. And 2 cubed t of n minus 3 will also be cut by the immediate next value on the next line, which I have not written in this series. 2 to the n minus 1 t of 2 will also be cut by the immediate previous line here, which I have also not written. This will also be cut by this. And we just need to write down whatever remains in this whole equation series. What remains on the left side is just the initial t of n. That's the singled out term on the left side remaining. And what will be there on the right side are these values, these powers of 2. So it writes 1 plus 2 plus 2 squared plus 2 cube, all the power of 2 in each of these lines. 2 to the n plus 1 plus 2 to the n. That means the summation of this series, the summation of all the powers of 2 to the power 0 up to 2 to the n, is the time complexity of our function. And if you remember from your high school classes, this is 2 to the power raised to plus 1 minus 1. So that's actually the time complexity of the recursion of Fibonacci series that I just wrote down. And if we put it in a big O notation, we just write to the end, because we always ignore constants. There we go. The reason that the method is called substitution is because of this cutting. All the values are being substituted from the previous one. And then at the end, when we sum up all the lines in the equation, the system of equation, there just remains only one term on the left side, which is the eventual value that we need to find. And there should remain a series of numbers which can be resolved using a formula. Okay, so that's the first example of substitution method, recursive time complexity analysis that I'm giving you. Now let's do another one. It's a practice task. The more you practice, the clearer it gets. Let's do one more recursion, which says this. What does it mean? Means we have some recursive function, let's call it recursive function, whose time complexity we are going to find. And in the recursion, there are two recursive calls of n-1 somewhere in the recursion. They doesn't necessarily need to be exactly n-1. It could also be n-2, just from the approximation we did. And there's a linear time loop somewhere in the function, which makes the additional time complexity of n. And we want to find the actual complexity of this recursion. So the first step is again write a generating function of the time complexity. So T of n is the time complexity of this recursive function with parameter n. And what we are writing here is the time complexities of doing the recursion calls and doing the loop. So now let's solve it. So the system that we applied, the last example will also be applied here. Twice T of n-1 is a single T of n-1 would have been twice T of n-2 plus n. So we can multiply this whole part with the 2 gives 2 squared T of n-2 plus 7. And then there are 2 squared T of. So a single one would be twice 2 of n-3 plus n multiplied with 2 squared, giving us 2 cubed T of n-3 plus 2 squared. Oh, mistake. This will not be n, rather it will be 1. The actual value in the call, and this will be n-2. Right. Coming down to due to the n-1 T of 2 would be to the n T of 1, 2, and n 1 be just to the n times 1. Again, this is the base case. So do the summation as we have written methodically. Well, they will cancel out each other. Cancel out, cancel out. The next line cancel out with the previous line. Cancel out, cancel out. There will only remain one single term on the left side, and there will remain a series of numbers on the right side. Equals n twice 1 squared. So coming down to the n minus 1 multiplied by 2. That's the time complexity of, that's the actual time complexity of this function. Now, what's remain is put a formula for this series, which is not trivial, not straightforward here, but from this one and from our uh, basic knowledge, we can say, let's say this is just 2 to the n, this is also 2 to the n. The actual thing should have 2 to the power n plus 1 somewhere, because the power of 2 is here present. And then in every term, there's a version of n multiplied. So maybe we can also write this one as the time complexity. Let's do one more. I will put some examples for you here. Let's say, what if t of n is t of n minus 1 plus n? There's no quotient here, just a single recursive call, this, and then a linear tempo. And then we always assume that the base case has constant time complexity. Base case can also have other time complexities sometimes, but let's assume that it doesn't. It has constant time complexity. So solve this to practice the substitution method. And you can make far more examples by yourself. In fact, we also have a lecture file on this topic. Check that out from our lesson plan. There are a few more examples there. And then there's also a PowerPoint lecture on how to apply substitution method for each of those examples. Let's do one from the algorithms that we have studied in this course. That's a binary search. First, write the time complexity of binary search using a generator function. Okay, equals to, what can we write here? In binary search, there's a recursion call. First, there's a logic that tries to divide the input in two equal halves, and then selects one of them and removes the other. So that takes constant time. Doing the calculation of mid and deciding which side to go, left or right. That's all constant time operation. And then we need to repeat that on the side that we have chosen. If we have chosen the left side, we repeat the same thing on the left side. If we have chosen the right one, we repeat the same thing on the right one. So that's the recursive part. Then the recursive part should have t of n by 2 as time complexity, making this the recurrence relation of the time complexity of binary search. I just used a new term for you, recurrence relation. That's another name for this generating function of time complexity. So whenever you see a recurrence relation of time complexity, assume that we are talking about the same thing here. All right, now let's solve it. I can go on and write d of n by 2 equals to d of, this should be n by 4 plus 1. D of n by 4 equals to, should be d of n by 8 plus 1. And then so on and then so on, bringing it down to, it will eventually go down to 1. It should be 1. The base case of binary search. And before that, you have to be 1. So, and we can say that we add up all the terms here, and these ones should cancel out, cancel out, cancel out. and what remained be t of n. There will always be one single term t of n remaining on the left side. If not, you must have made some mistake. And on the right side, there will always remain a series of numbers. In this case, these are all ones. These ones. So 1 plus 1 plus 1. And we just need to find out how many ones are there. So the question is, how many lines have we written here? How many lines? That should be the number of ones finally. So which is the number of lines that we need to write to get n reduced down to 1 each time, dividing it with the 2. N becomes n by 2 in the next line, n by 2 becomes n by 4 in the next line, n by 8, n by 16, and going very down to 2 and 1. So from our common sense, we know this is log. That let's find a more soothing way or visually pleasing way to write it down. I will write the function again. T of n is T of n by 2 plus 1. Now, what I will do is assume that n is some power of 2. Let's say n equals to 2 to the n. We don't know the value of n yet, but we are assuming that the n, which was given to us, can be written as a power of 2. All right? So the equation rewrites as t of 2 to the n is equal to t of 2 to the m minus 1 plus 1. This is actually dividing n by 2. 2 to the m divided by 2 is 2 to the so and t of 2 to the m minus 1 is continuing forward. 2 to the m minus 2 plus 1. This will go down to t of 2. The power is just a single one here. T of 2 to the power 1 is equals to t of 2 to the power 0 plus 1. T of 2 to the power 0 is just 1, which is the base case. Okay, now let's substitute again. All these will be cut down. I'm not doing that again. So on the left side, just remains not this line. I'll start from here to the m is equals to. Now we know for sure how many lines are here. As the power of 2 goes from m to m minus 1, m minus 2, decreases 1 in each line and goes down to 0. There's just m lines here. So that means we have n ones. So t of 2 to the m is equals to m. And the value of m is, I'm sorry, it was my son. And the value of m should be figured out from this assumption. M equals to 2 to the power n. If we apply log here, log based 2 to the m, the m equals to d. So, there you go. So few more examples in this format would be figure out the time complexity of merge sort using this. The first step is always write down the recurrence relation. In merge sort, we divide the array in 2 equal halves and we apply recursion on both sides. So that's twice t of m by 2. Plus, we have to merge the answers together, which takes a linear time. So that's the recurrence relation. And if you want to solve, you will eventually get n log n, which is the time complexity of merge sort, and you can get it using the substitution that as applied here. And the trick is, whenever we have n by 2 in the recursion, or n by something, n by some value k in the recursion, we should always start by assuming n equals to some k to the power n, to put it in the template of the substitution. That's it. That's the substitution method. We also need to learn one more method to figure out time complexity of recursive functions, which is master theorem. I'm sorry, give me 1 minute to talk to my son. He seems agitated for some reason. Coming back in a minute. Okay, I'm back.
Sure.
হ্যাঁ বলে ফেলো।
তার আগের এক্সাম্পলটাতে আপনার লাস্টের দিকে একটু বুঝতে সমস্যা হচ্ছিল।
এটা দিস ওয়ান
ইয়েস স্যার।
কোনটা বুঝো নাই? যে পরে যেটা বললাম যে মার্জ
যে
সর্টারটা কিভাবে করে?
না, যখন আপনার লগ টু বেস এন ইকুয়াল টু লগ টু বেস টু টু দি পাওয়ার এম,
ও আচ্ছা, এম এম এর ভ্যালুটা কিভাবে বের করবো সেটা আমরা প্রথমে অ্যাজিউম করে নিছি, অ্যাজিউমিং n ইকুয়ালস টু 2 এর কোন একটা পাওয়ার m, m এর ভ্যালু জানি না আমরা। তো তো পুরো সাবস্টিটিউশনটা করে দেখা গেল যে টি অফ টয়েস m ইকুয়ালস টু m আসে। টয়েস m মানে তো n, মানে টি অফ n ইকুয়ালস টু m বলতে হয়। তো m এর একটা ভ্যালু বসানো লাগবে। m এর ভ্যালুটা কিভাবে পাবো? এই অ্যাজাম্পশনে লক করে দিলেই তো m এর ভ্যালুটা পাওয়া যাবে। এই দেখো এখানে লগ টু বেস টু টু দ্য পাওয়ার m, তো যে লগের নিয়ম অনুযায়ী যে আমরা বলি যে এই এমটা সামনে চলে আসবে, তারপর লগ এর বেস টু আর প্যারামিটার টু, এটা 1 হয়ে যাবে। বুঝছো?
ইয়েস স্যার।
m ইন্টু log টু টু, এটা 1, সেম ইকুয়ালস টু log টু বেস। ওকে, মাস্টার থিওরেম। মাস্টার থিওরেম দিয়ে এই কাজগুলো করা খুব সহজ। ইটস ভেরি ইজি টু অ্যাপ্লাই মাস্টার থিওরেম বিকজ ইটস জাস্ট এ if else formula. If this, then this. That's what master theorem is. But the downside of master theorem, I will show you what the actual formula is. মানে এই if else logic এর ভিতরে কি লিখতে হয় এটা আমি দেখাবো এখনই। Let me first tell you the downside. The downside of master theorem is it can only be applied for divide and conquer algorithms. The algorithms that fall under the divide and conquer category. All the examples that we have done in this class, this is an example of divide and conquer. This is binary search, but we can take it as an example of divide and conquer. Merge sort is also a divide and conquer technique, but this one was not. This one was not a divide and conquer technique. Uh, The observation here is how n is being reduced in the recursion. আমরা এখানে n থেকে n minus 1 এ গেছি। We reduce n to n minus 1. And in divide and conquer, we reduce n by dividing it with some values. That's the core concept of divide and conquer, no? That if you have a large input, you divide the input in a few parts. It can be 2 parts, it can be 3 parts. And then you solve the same problem for each of those parts, and then somehow get one single answer from all those answers. So in every example of divide and conquer, if you write the time complexity down using the reconciliation, T of n would be T of n by something. There can be another question, that means how many parts are there. So there will also be some question value here. And then there will be some additional time complexity. If the reconciliation is in this format, exactly division, then only we can apply master theorem. If n is reduced to n minus something, then we cannot. Okay, let's first see some examples. Let's say in merge sort, or in quick sort, or in maxsum subarray, we divide the input in 2 parts. So divide. Each part has equal halves of the original input, and then there are 2 parts. And then we do some works. In merge sort, we do merging. In quick sort, we do the partition. In maxsum subarray, we do the cross sum, which takes linear time complexity. So the time complexity of all those 3 algorithms, techniques, can be written as this single reconciliation. It's a bit different for binary search, which we just saw here. It's a bit different for ternary search, which would be T of n is equals to of. In ternary search, we divide the input in 3 parts. We divide as 1/3, and then take just one of them. We don't go to all 3 parts in ternary search or even in binary search. And extra operations that we do in ternary search just take constant time complexity, which is basically the comparison questions. Where should we go? এই ফরম্যাটে হলে মাস্টার থিওরেমটা অ্যাপ্লাই করা যাবে। Now let me write down the if else logics in master theorem. আমি এই জিনিসটা একটু নেট থেকে বের করে তোমাদেরকে দেখাই, তাহলে তাড়াতাড়ি লিখে ফেলা যাবে। I will quickly go to internet, যেটা তোমরা দেখতে পাচ্ছ না, আমার স্ক্রিনে শেয়ার করা নাই। তো ছবি বের করে এনে আমি আবার স্লাইডটার মধ্যে ফেলি। I am just searching internet for master theorem's equation. তোমরা আমার স্ক্রিনে দেখতে পাচ্ছ না, হয়ে যাবে। The screen should be back. এই হচ্ছে মাস্টার থিওরেমের ফর্মুলা। তো লেট মি ব্রেক ইট ডাউন ফর ইউ। তোমরা পরে একটু নিজেরা একটা ভালো ছবি দেখে বা কোন একটা জায়গা থেকে এটা পড়ে নিও, বাট লেট মি break down what's written here. Master theorem says we first need to write down the time complexity in a recurrence relation or a generative formula, as we have already studied. And it should also write what's the time complexity in the base case. Say the line আমরা already দেখে ফেলছি। And then see that there are few variables here. This is an A, this is a B, and this part is written in a term C multiplied by n to the power k. C multiplied by n to the power k. Master theorem uses these variables to make the if-else logic A, B, C, and K. And the logic is here. If A less than B to the K, A less than B to the power K, then the time complexity is this. If not, if A equals to B to the power K, then the time complexity is this. And if A greater than B to the power K, then the time complexity is this. So it's just three cases. Case 1, case 2. I'm writing the same thing down again. Case 3. If that, then that. If A less than B to the K, then time complexity is theta of. We all know what theta means in asymptotic notations. With the type bound time complexity. If A equals to B to the K, then time complexity is theta of into the K log n. If A is greater than, so it's just between this variable A and another value B to the K. If one is less than the other, or if both are equal. It's a theorem. So it's understandable that there's some form of mathematical setup here. এবার একটু প্র্যাকটিস করি। Let's do it using Marshall. Marshall's time complexity we wrote as twice t of n by 2 plus n. So let's figure out what's A, what's B, what is C, and what is K. The format of Master theorem says T of n is equals to A times T of n by B plus C multiplied by n to the power k. Okay. The value of A is this one, 2. The value of B plus 2. The value of C is what's there in this line as coefficient of m. That's a 1. And value of K is what's there in this line as the power of n. That's also 1. Yeah. Now you just put these values here to find out which case this belongs to. কে বলতে পারো এটা কোন কেস হবে?
Second case.
Case 1, 2, or 3? কোনটা?
2.
Case 2. A equals to B to the power k. So the time complexity will be theta of n to the power k, case 1 log n. Just like that. দেখো কোনো সাবস্টিটিউশন, কোনো ইকুয়েশন লিখতে হলো না, কোনো ইন্টিগ্রেটিভ অ্যানালিসিস করতে হলো না। We just put some values in a if-else logic setup, and then it will give us the time complexity. আরেকটা করি, let's do with finite search. T of n is t of n by 2 plus 1. What's value of a? T of n by 2 এর আগে কি আছে? 1. What's the value of b? 2. What's the value of c? c কি হবে বলতে পারবা কেউ? This will be a 1. And what will be the value of k? k কি হবে? এখানে n তো নাই, এখানে আছে 1. So we can write 1 as n to the power 0. That means k is 0. Right? So again, a is 1. b to the power k is what? 2 to the power 0 is also 1. That means again case 2. The case 2 তে যা হয় সেটা লিখে হলো। Let's do one more. What if t equals to t of n equals to twice t of n by 3 plus 2 times square root. We don't know which algorithm can have a time complexity like that, but let's say something does. Let's find out what the time complexity actually is. Again, a equals to 2. That's all we need to do when we are using master theorem. A equals to 3, c equals to 2, k equals to 2. So এর সাথে b to the power k রিলেশনটা বের করি। a b to the k is 2 b to the k 3 square. So this is less. Less means this will go to case 1. Then the time complexity would be n to the power of n to the power square. Without actually knowing what the algorithm is, we know what time complexity this has. So our practice should be apply this for all the different concrete algorithms that we know. Merge sort, quick sort, maximum subarray. Merge sort and maximum subarray are same. Quick sort is also same. Then binary search, ternary search. We also know another different concrete algorithm called Karatsuba multiplication. Karatsuba multiplication টা করে দেখাই তোমাদেরকে because I have 5 minutes time left. Karatsuba multiplication কি করে? দুইটা ইন্টিজার কে গুণ করে। It multiplies two integers. So time complexity টাকে if we write t of n, then we need to find out the setup, how those numbers get reduced. I don't know if you remember, but in Karatsuba multiplication, if the numbers are n-digit numbers, we make them, if the numbers are x and y, we take x0 and x1 from it, make two halves of this number, and then make two halves of the other, two equal terms. So the numbers are reduced to n by 2-digit numbers. And then we somehow derive a formula from it to get x times y by doing 3 multiplications. You can go back to the lecture of Karatsuba algorithm to find this out, but eventually we get the value of xy, x multiplied by y, using 3 multiplications of x0, x1, y0, y1, so on. So that's 3 recursion calls, plus the additions, shiftings, whatever work left, which is just constant. So that's the reconciliation of Cart's form operation. And you apply it here. I've told you before that the Karatsuba multiplication has a time complexity of n to the power 1.58. So check that whether it matches. That's it. That's almost everything that I plan to discuss today. I'm sorry that we had to do this in an online class. Because in a physical class, I would have given you some classworks to do and then we could learn instantly. But now you have to get back to this lecture when I pause the recording in class and check again. If you have any questions, you can say it now or I don't have this. Okay. Bye-bye.
Okay, sir.